and how we can define a string. A string, in some sense, you can also think of as just being a sort of particular kind of an array. It's an array of characters, okay? But we could just as easily make an array of anything else, okay? And then there's a bunch of functions that are built into C for doing the kinds of things you might expect to do with strings. So, for example, we could say, let's do, let's see. Okay, we can, and what kind of number is this going to be? An int. And we could also print something like that. Okay, so what does string length do? What do you think? Yeah, it just gets the length of it. Okay. All right, so let's run this and kind of talk that through. All right, so where are we? Documents, examples, string. All right, so we need to compile it. And I'm going to go ahead and throw in the debugging and the static flag, even though we don't really need that for right now. Let's see, what did I forget? strlen. Did I make a typo? Oh, attempting static link of dynamic object. Okay. And we need the header file for that. Okay, so let's, try that. Okay, so we can't statically link that. So let's just get rid of that for now. Okay, fine. Okay, why did it not print my string length? Did I save it? Okay, I saved it. Okay, I'm not sure why that happened. Int length is string length, my string. Well, crap. Okay, I'm not sure why that's not working. What did I manage to mess up here? Well, unless it wants, I don't see why that would matter. Okay, I've screwed something up here. Well, okay, there's one thing we can do. Let's try this. Oh, okay. Well, I am just smoking it this morning, so sorry. Huh? LEN? I don't think so. I think it's going to be strlen. That's the function. Yeah, okay. I'm not sure why that's not working. Huh? Well, okay. We could do that, right? So let's just roll our own thing to calculate the length. Okay. How would we do that? Huh? Yeah, exactly. So if it's an array of things, we can just go through and count them, and then how do we know if we've hit the end of it? Right, we should expect to see that null terminator. Okay, so for example, let's just do something. Now, in this case, we know that the thing is 6 long because that's how I defined it. Okay, but why don't we do let's make a for loop. Okay. Not equal to the null terminator, right? Yeah. Okay, so that certainly works. Let me just do the for loop just for a moment. We'll switch it to what you're saying because what you're saying makes more sense, right? Because for me to write this with a for loop, I have to know what the length of the string is before I do anything, and of course that's the whole point of doing this loop in the first place, right? So it's kind of circular reasoning. But what I just wanted to do for right this instant though was let's print just one letter at a time, okay? And okay, and then which character are we going to do? We're going to do my string of I, okay? And let's just go through this. Okay, what? Am I just smoking something this morning, guys? Oh, okay. I see. We're just being idiots. No? Okay, you know what? Let me just... right, which that I'm okay with right now. I just want to print it character by character. We're not only we're not printing the length, but we're never actually updating its value at this moment. Oops, a semicolon, of course. That's why you don't program at 8 in the morning. Okay, something is seriously messed up here, guys. What? Am I crazy this morning, or like what on earth is going on here? Well, yeah, like why wouldn't it be going into this loop? I is 0, I less than 6. This one? Oh yeah. That was common. Oh my goodness. Okay. I know what's wrong. Look what I'm typing here. What should be immediately after the O? The name of the, yeah, string one, right? The name of the program. So I was outputting this thing to a file called -G. Okay, let's try this again, shall we? Let's just do that. There we go. Okay. So, all right, let's go back to this. Okay, and let's do for while we're at it here. Let's go back to what we were. Right, that, and then what were we going to print? Oops. This, yes. Okay. Did I forget something? No? Okay. Okay, so there we go. All right, so let's clean this up a bit. Let's get rid of this little thing that I just threw into test. Make sure that we were going into the loop. Okay, and what do we get for our length? 5. Okay. Now, but if you notice here, what is printed after the O? Yeah, an empty space, okay, because probably what's in memory at that location is just a set of all zeros, right? So if I do something like, let's just make that a ridiculous number, right? Then I'm going to get a bunch of things. Now, they look blank because they're non-printing characters in ASCII, okay? That doesn't necessarily mean that they're all zeros in memory, okay? Did I pull up an Ascii table last time just to put on the, right? So there's a bunch of the things at the very beginning, the first, 20 or 30 of them, that are characters, but they're not printable characters, right? So things like transmission received, transmission sent, Null Terminator, right? A bunch of things that would be used in communication between devices are also there in ASCII. Okay, so like I said, just because there's a blank there doesn't mean that it's not, or doesn't mean that it's necessarily 00 in the ASCII. Okay. Okay, so great. Now, on the subject then, so we've got this string length thing, right? Oh, and did it print the string length, by the way? Well, yeah, it did. Okay, 5. So what would happen if I removed this? Okay, what happened? It was still 5, right? Okay, so I changed, I didn't say in advance how many characters were going to be in this array, okay? And now there's one thing that I guess is kind of nice. Well, it's both nice and not nice, because really, how long is that string? Yeah, because we got to have the null terminator to worry about. Okay, but if I like, when I'm thinking about the string, if I'm thinking about the characters in it, do I want the null terminator or not? Well, that's kind of, how are we going to define it? Okay, but of course it should be there. And so, point being, here, this very first blank should be the null terminator. The rest of them, who knows, right? Just depends on what's in memory. Okay. Okay, so what about the the for loop to compute the string length? That's a good point. Yeah. Okay, I'd want to use a while loop because if I don't know what the length is in advance, then I can't use a for loop because I don't know how many times to do it. Okay, so what might we do something like there? While, okay, is not, and that brings us to a fun one. Not equal is exclamation point equal, right? While string of I is, okay, what's first automatically the problem that I'm going to have here? Huh? What's I? Nothing. Okay. Where is I? I have defined it here, but does it live anywhere else? No, it's out of scope. So before I do something like this, let me use J. I need to initialize my counting variable, okay? Because otherwise, string of J is sort of an undefined, well, what is J, right? Okay, so while string, the element of the string is not equal to what? Okay, the null terminator. Now, what is the null terminator? That. Okay, and here's where we have to be a little bit careful because there's a few ways we can look at this, but an array, right, a string is an array of whats. What data type gets repeated? What data type is used to build a string? A string is a bunch of characters, right? Okay, well, does it make sense to talk about two characters being equal? Not really, right? We talk about numbers being equal. Okay, now, yes, each character you can think of as being a number. It's an 8-bit number, right? Because this is an ASCII. All right, but we've got to make sure that we're comparing sort of valid data types. Okay, and what should we do here? What should our loop do? Right. So I've declared the counter here, right, to be 0 right before, and then what do I need to do? Yeah, j equals j plus 1. Hmm? Oh, yeah, thank you. Not string. Yeah, good. Okay, good. All right, and then what do we want to do at the end here? Yeah, so we'll printf, this is an integer, and there. Okay. Yes. Hmm? No, we goofed, but not really. Okay. So let's look at what the error is, because that actually is a good way to talk about what the next kind of thing is. Okay, so warning, comparison between pointer and integer. What is a pointer? Sort of. It's a little more than that, yeah. Yeah, exactly. Okay, so when I say my string of 0, okay, like on the one hand, we can think about that as just being whatever the first character of the array is, okay, and it is. But if I think about what my string like is, okay, really it's just a segment of things in memory, okay, and the base address of the string is wherever the first character is. Okay, so that's a memory address someplace. Okay, and then where's the next character relative to the start of the string? Well, okay, let me back up. Let me back up and do one other thing, and we'll come back to this loop. Because the compiler just basically says, "Oh, how many things are there?" and it does it, deals with it for you. No, we did. I mean, I yeah. I mean, so this is the compiler, right? Well, two things, right? We're writing in C, right? So it's a little higher level. We can be a little loose, or so. When we define these strings in when we do this in straight assembly, we'll just define what the string is. There's no length associated with it in terms of its definition. You just say it's this thing, okay? And in terms of assembly, right, we're just going to be working directly in the memory, and we don't have to kind of define that in advance. Okay, so let's see. Let me comment this stuff out for a moment, and let's sort of talk about what a pointer is. Okay, so if I let's see, which way do I want to do this? This would be int address equals no, ampersand for my string, and then Oops. Okay. Okay, hold on. Hold on 1 second. I'm being a bonehead this morning. Oh, yeah, okay. It's not, let me just do it this way. Oops. Okay, there, and, okay, why is it complaining about that? \x used with no following hex digits. Oh, God, I'm an idiot. Percent. It's %x, not \x. Okay, so here we go. All right, so what printed here? Yeah, okay, so the location in memory where the string is stored. Okay, now this is the base address of it. Okay, so what I find in memory in that particular little spot, I'd find H, and then what's in the next cell? E, and so on. Okay, so the length of these things, or sorry, not the length, but each successive character is of course stored in the next byte of memory, and we can actually see this if we run this. Let me throw the debugging stuff back in here and not screw it up this time. Okay, so let me do. Okay. Oh, okay. Hold on. I need to. Let me put a breakpoint at line 26. Oops. Okay, so I got there. Okay, so don't worry about what I just typed here. We'll get to that later. Okay, but where in memory did this thing say that the string had been stored? FFFFF060. Okay, whatever, right? And if I look, right, at FFFF060, what's there? That's not correct, because that should be, sorry, hold on. What was it? FFFF060. Oops. Oh, okay. It's going to be. Zero F7. Oh, here? Did I just forget? No, there should be. Yeah, okay. So this is where the string should be stored, but it's because what should we see for hello? What's capital H in ASCII? Well, let's look it up. See, this is why I don't like working in C. I like working in assembly because everything is much more clear to me in assembly. All right, so Ascii table, what did we say? Capital H is in hex 48, right? So what should we be expecting to see? 48 followed by 65 and so on, okay? Which is not what we've got. Okay, so we're not in the correct location in memory. Huh? Oh, God, thank you. Okay. Yes, okay. This is something, it's been a little while since I've done this, so, right. Okay. When you look at memory, particularly in the debugger, there's, um, here's sort of the problem, right? So let me just write up a random number on the board. If I could find a piece of chalk. Okay, what does that number mean? How do we interpret that? 371. Okay, you're not idiots. You all know how to do this. Okay, which side, where's the most significant digit of that number? What is it? 3. Okay, and where is it? It's on the left. Okay, when things are displayed in memory, okay, well, okay, so this looks backwards, okay, but if we think about it, right, so at this address, what's the first, so really, how many things are here? How many memory addresses are represented in that little chunk of stuff? 4, right? Not 1. Yes? Okay, so where's the least significant thing? That would be the thing in the lowest memory address. It's here, right? It's like the 1 in my number on the board. Okay, so what is in memory cell 7FFF blah 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 060? It's 48. What's in blah 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 61? 65, 6C, 6C, and then what? 6F, which is the little lowercase o, and then followed by the Null Terminator. Just garbage. Yeah, nothing special. Well, okay, actually, that's not maybe entirely true because what's here? 5. Does 5 have anything to do with our program? Yeah, it was the string length that we calculated, and because we stored it in a variable, that got stored in memory someplace, and it just so happens to be just sort of right there adjacent to it. Okay, now as for all the other stuff, that's as far as we're concerned, garbage. Okay. What now? Somebody said wait. Sweet. Okay, not wait. Okay, so the um, the the memory location, right, does have our string. Okay, so so let's go back to this error that we encountered a minute ago before I commented everything out and sort out what is going on. What does it mean? Okay, so let me uncomment this out. Okay, and let's go back and let's look at what error it gives me. Okay, warning, comparison between pointer and integer. Okay, so I guess this sort of begs the question, what is, okay, it says I'm comparing a pointer and an integer, okay, and So why don't we actually do, let's do this actually. Oops, sorry. I meant to just run it. Okay, there. Did I ever print this? Why did it not print? Okay. Oops. Oh, program's crashed. We got ourselves into a nice infinite loop here. Okay, so what's going on? Why are we getting into a loop here, right? What do we have to do to compute? Or so the issue is this comparison, right? How do I, so my string of j, okay, what is that? Right, so let me comment this back out. Oops. All right, so let's do, let's just do this, okay? And I'm gonna get rid of this loop because we don't need it anymore. Okay, so what is my string of 0? Oops, sorry. Okay, what is my string of 0? Yeah, the capital H, okay? So here it's printing here as a character, right? Interpreted in ASCII, okay? So what we need to figure out, right, is how do I compare a character to the null terminator? Like, how do I know if two characters are the same? And this is what I'm blanking on. Dot equals? Let's see. What now? Okay, but we want not dot equals. So it's, okay, well, let's find out. Oh, this? Well, but we want it to be, okay, hold on. Let's just take a quick Google. Because I'm being a complete moron. No, that should work. Text of I. Okay, so why? So what? Now what we want here is not equals. Oh. Sorry, it should have been a single quote, not a double quote. Well, maybe. Huh? What now? No, I did it right this time because dash O, my string not equal 0. It should. Okay, unless I'm doing something stupid here. Oops. Yeah, so it's going into an infinite loop there. And I thought that was, why is this not working? Backslash 0. This should work. Okay, so what am I screwing up here, guys? So here? Well, that'll work, yeah. But that shouldn't explain why we're in an infinite loop. Well, although it does. Okay. Oh, no. I know what happened. Yeah. Okay. So j equals j plus plus. What is that going to do? Well, yeah, j plus plus add 1, but then it reassigns the value of j. Okay. So I think what that would do then is count by 2's. Would it? Yeah, and skip over the null terminator. Okay. In which case, it's going to be going to God knows where in memory to figure out, and then load something in and say, well, what's this? Well, it's not the null terminator. Okay. All right. So yes, I need more coffee. All right. So let's see what we got. There we go. Okay. So what is this doing? Well, goes through, right, picks out a single character from the string and compares that to the null terminator. If it is the null terminator, that means we've hit the end of the string, we're done, okay? And if we increment each time our counter, then great. Okay, now, what's the only other thing that I have to do though is that if I'm gonna use a while loop, I need to declare the counting variable before I enter the loop, right? Unlike a for loop where you kind of do it as you go, right? Okay. All right, so does that kind of make sense now that I'm not being a complete bonehead? Yes? Okay, so the pointer thing, let's go back to that. And let's talk more specifically, okay, what's happening on this step right here where we pass the string to the function that C happens to have built in called string length. Okay, great. Can I pass a string to a function? Well, I sort of just did, okay? Or at least it appears that I just did. But I guarantee you I really didn't just pass a string, okay? Because let's say, for example, that my string had 1 billion characters in it. Okay, that's not reasonable, but let's just suppose. Does the processor have 1 billion spaces of memory? We might in RAM, okay, but I can't just pass whole chunks of memory around, okay? So this is when we're going to start talking about the assembly here next week, but this sort of gives us taste to it. The way that parameters get passed to functions and data gets passed back and forth is, so inside the processor, there are like when you get down into the tiniest part of it, okay, so not cache, not L1, L2, L3 cache, not RAM, none of that, right? Just the processor, the core itself. There are some number of little memory cells, okay? The exact number depends on the architecture. And these things are called registers, okay? They are extremely fast to access because they literally are in the processor. They're not cache, they're not RAM, they're right. But there's only some of them. Okay. Now, depending on the architecture, you could have a fair number of them or not so many of them. Okay. The ARM architecture, the 64-bit ARM architecture anyway, has 32 integer registers, each of which can be 64 bits wide. Okay. It also has 32 floating point registers, and you can do some vectory stuff, and there's all kinds of fancy stuff. But for our purposes, if we're not doing anything with floating point math, basically there's 32 of these registers. Now, some of them have special purposes. So, for example, one of them is reserved for use as what's called a stack pointer. We'll talk about that later. and one always reports 0, okay, which is useful. But those fundamentally are what you have to process with. Just 64-bit or just little banks of memory. Okay, so if I've only got 32 of them, or it really doesn't matter how few or how many I have, I don't have a billion of them, right? And so if I want to tell a function to do something on a string, I can't pass the entire string to it, just like here, pick it up and here you go, right? What can I do if I've only got 32-bit, 32 of these registers? I can put 64-bit numbers in each of the registers, okay? And I can use that to tell the thing where the data is that it needs to process on. And then if I'm not an idiot, the function that I'm passing this data to, if I'm the one writing it, cannot be stupid about how it then takes that data and then does something with it. Okay, so for example, the string length function is probably, basically something along these lines, right? What else would it need to be? Okay, but in terms of how it gets there, I'm not passing it the string. I'm passing it a reference to the string, and then the function goes out and finds that string in memory and does whatever it needs to do with it. Okay, and so what I'm passing here is, in this case, a single number, its memory address. Okay, maybe if we wanted to be fancy, we could pass, this would be silly, obviously, but let's say we wanted to write a function that would take a string and change everything to uppercase, okay? Then maybe we could say, all right, here's the string, and I want you to do this to the first 10 characters, okay? Then how many parameters might we be passing? The reference to the string and the number of characters we want it to deal with, or whatever, right? Okay, so if you want to pass data between functions, right, what you're really doing is when the processor then gets to the code for the next function, that function is going to be expecting that the registers have the appropriate either values or addresses for the things that it needs to process with. Okay, but you've only got 32 of these things on an ARM processor. On a 32-bit ARM processor, you only have 16 of them. And if we go way back to my favorite processor of all time, which is, yeah, that's MOS 6502, right? It had 3, and really, in some sense, only 1, depending on how you count. Okay, so it was very, because the other 2 you could only use in certain ways, and yeah. So point being, though, you had to pass things by reference rather than the actual object themselves. Now, if your function is passing numbers back and forth, those will fit in the registers. And so we can just pass the actual values. We don't have to pass pointers. Okay, but strings are too big, right? So that's not going to work. Okay, so does that kind of make sense? And in fact, let me go back into GDB here. Okay, so I showed you what the contents of memory were. Okay, here's all, well, let me blow this up so it's a little easier to see. Here's the contents of all the registers. Well, there's more, obviously, that are below the page there. Okay, and from our perspective, most of this looks like what? Do any of these numbers mean anything to us? Not really. Okay, I don't see anything that's particularly important there, with the one exception of there just so happens to be a 5 right there. That may or may not be coincidence. Okay. Um, yeah. So, and we'll talk about like how do you know which register to put a pointer in before you transfer to a different function. There's a convention for that. And so we'll talk through all of that. And then there are some special registers down there, SP stack pointer and PC program counter. Also, then there's the 3 status registers below it that are sort of tell you various things like, did the operation you just did it overflow? Was there a carry? That sort of stuff. Okay. Now, how many of you guys took 101 with me? Okay. So you guys remember doing the Brookshire assembly? Vaguely? Okay. Right. It was. Well, now we're doing it for a big boy processor, right? Um, so this Brookshire thing, right, was for those of you who didn't take 101, is sort of a simplified processor, a simplified instruction set, and basically meant to give you a taste of what assembly means without having to go balls deep into real assembly. Okay. Um, and there was a program counter there. Okay. There was no stack pointer. There were only 16 registers. There were no flags, right? The author of this stripped out a lot of it in order to make it more accessible to 101 kind of class. Okay. Anyway, so parameters are going to actually get passed for most things as pointers, unless it's just integer or floating point values, and it's only a few of them, in which case you can just actually pass the numbers. But for the most part, then you have to do it with pointers. Okay, so even though it doesn't look like I'm passing a pointer here, I really am. Okay, and in fact, what I can do is let me do say break 7 or 8. Okay, so it's about to do this instruction. Okay, and if I look at what's in register 0, yeah, a memory address. Okay, that happened to be the exact same number as it was before. Sometimes, by the way, when you rerun this, it doesn't necessarily go to the same place in memory, right? That's just going to depend on the operating system. Okay, so, but point being, 7FFFF060, was that a number that we recognized before? Yeah, it was, right? It was the location of our string, okay? And this, so the address was put into register 0, and then I'm about to run the function string length, okay? And what is string length expecting to come into it? The address of a string. And then it's going to go say, okay, you gave me the base address of the string, not 0, not null, not null, not null, not, and eventually it will finish, okay? In which case, okay, it finishes, okay? So now let me do, what line was that on here? Let me do a break at line 9 right before it prints the string. Okay, what's sitting in register 0 there? The number 5, which is the output of the string length function coming back to us. Okay, so the convention here is you you basically put parameters starting in register 0, and then they come out starting in register 0, and then up through 8 of them, in which case, if you use more than 8, then you've got to start using the stack. We'll talk about all those details later. Okay. All right, so that's kind of the crash course as to what a pointer is. And then let me step one spot. Well, okay, so I can't do that because I didn't statically compile this, but okay, we'll talk about that later. All right, so that's the sort of crash course idea of what a pointer is, okay? And if, now a pointer, in terms of what kind of data type is it, it's still an integer, okay? In our case, what kind of integer? How many bits? Huh? 20? How many bits would a pointer need to be on this machine? Well, what is it pointing? What does a pointer point to? No. Something in memory. It's a memory address. Okay. So on this particular architecture, memory addresses are how big? 64 bits. Okay. Which is why, well, one reason we say that this is a 64-bit architecture, though there's some, yeah, okay. Now, if we were to do this on modern Intel, so on the laptops that are in the room, how big would the pointers there be? Also 64 bits, okay? If we were to do this on a computer from the mid-90s, they'd be 32 bits wide, okay? And it was sort of in the early to mid-2000s, right, that you started like having the difference between 32-bit and 64-bit versions of OSs, right? So why was it that we had to use this beta version of the operating system, by the way? Okay, the actual like real version of the Raspberry OS, what's the problem from our point of view? It's only a 32-bit OS, okay? And so now it's nice because that version comes with all kinds of programs like hell. It even comes with a full version of Mathematica, like for free, which is awesome. But there is no 64-bit version for Mathematica yet. I've been nagging the people at Wolfram about that because it would be awesome. Okay, so now I guess this begs the question, what's the advantage of 64 bits versus 32? I mean, other than more bits is always better if that's... Well, you can, it's not so much that you can store more memory, but you can address more memory, okay? What's the maximum number of cells of memory that you could address if you had 32 bits? 2 to the power of 32, right? What's 2 to the 32? Huh? 4 point something billion, okay? Well, 32 because if you're counting memory addresses, there are no negative memory addresses, right? So the number of values is 2 to the 32. The largest such value is 2 to the 32 minus 1, right? Because you start counting at 0. Okay, so what's 2 to the 32? Well, you do, if only we had like computers galore in this room. Wouldn't that be great? Yeah, okay. Or let's go to my favorite. Yeah. Okay. It's that many bytes. Okay. And so let's convert this here. How many gigabytes is it? 4 gigabytes. Okay. So in the mid-90s, was this a problem? Not really. But what happens when we got into the mid-2000s? How much memory is in computers nowadays? How much RAM is in these things? 8, maybe even 16 gigabytes? Okay, so the problem that we, the royal we, ran into in the mid-90s, okay, mid to late 90s, was memory was starting to become cheap enough that you could produce gigabytes of it on end, and the only way to address more than 4 gigabytes worth of memory is to have more than 32 bits, okay? All right, so hence why we have 64-bit OSs. So that, because for example, let's say that you had a computer with 8 gigabytes of memory in it, and you installed a 32-bit OS on it. How much of that memory would the OS actually see? Only the 4 gigabytes. That's it. It can't address any more than that. Okay, and for technical reasons, it was actually for most of the time 3.5, but whatever. Yeah, question? Good point. Okay, so the Raspberry Pis that most of you bought, and myself included, how much RAM do they actually have in them? They've only got 4 gigabytes. Okay, so it's not really a problem in that sense, except you can buy one of these with 8 gigabytes. Okay, so they do sell an 8 gigabyte model. I didn't tell you guys to buy them because there's like, heck, we could have gotten away with 1 gigabyte for what we're doing. But the 4 gigabyte ones are the ones that the most volume of those is, so they tend to be, the kits tend to be cheaper. Okay. Well, and if these things are going to be useful to you guys for years to come, particularly for like those of you who are doing physics and ad lab projects, or when you get into senior capstone for CS, right? I mean, you're going to find uses for these pies beyond just this class. That's my hope anyway. Okay, one other little thing here. What's the difference between a gigabyte and a gigabyte? Because this drives me crazy, but I'm old school, so I just use the old convention. How observant, Mr. Runge. Yeah. Okay. So what's the difference? You agree? Well, okay. What Owen said is not incorrect. It's also not helpful, but it's not incorrect. Okay. So what does the word giga mean? Or let's say kilo. Let's start there. Mm-hmm. Unless, okay, so if I talk about, say, a kiloton of TNT, right? Let's say I'm setting off nuclear weapons, as one does. Um, right? What does kilo mean in that context? 1,000 of those things. Okay, what's a kilobyte? Well, okay, it depends on who you ask, right? So back in the day, in the 60s, right? If I wanted to talk about uh, a larger unit of things, does 1,000 make sense when we're dealing with binary stuff to use as a multiplier? No. What would make sense is 1,024 because it's a power of 2, right? Well, 1,024 is pretty close to 1,000, isn't it? Okay, so the convention back in the day was, oh, well, that's pretty close to 1,000. We'll just use kilo for that, right? And you're only off by 24, so that's not really a big deal, okay? But then the difference gets bigger the higher up you go, okay? So a megabyte is then defined as 1024 kilobytes, and a gigabyte would be 1024 megabytes, and so on. Okay, but then the Europeans had to get involved right? Okay, because when and I'm exaggerating here, right? So what are we doing? We're using the metric prefixes incorrectly. Okay, and so this bothers some people. And so what was proposed was, okay, if you want to use metric prefixes, you're counting in powers of 10, not powers of 2. And then they renamed what everybody used to call a gigabyte to be a gigabyte. Okay, now, how many of you like to say the word gigabyte? It sounds ridiculous. It sounds stupid. Okay? Huh? All right, well, say wheat thins.
Huh?
So, say wheat. Say thins. Wheat thins. Say Will Wheaton. Okay. Will Wheaton.
It's too early.
Yeah. Okay. Do we all get the wheat thins joke? Do y'all get it from Family Guy? Yeah. Okay. All right. But no. My point though is that it sounds silly, right? And so a lot of people don't say it, myself included, okay? Because this gigabyte thing didn't exist when I was learning computers, okay? So back in the day, it was, what's a kilobyte? 1024 bytes. What's a kilo whatever else? 1,000 of those things. And you're just not idiots, so we just dealt with it. Okay, knowing that yes, we're kind of abusing the metric prefixes, but that's okay. Okay, this, by the way, does kind of bite you though, in this bite. You see what I did there? Yeah. Has anybody bought a hard drive recently? Yeah. What happens when you buy a hard drive? You get your 1 terabyte hard drive and then you format it in Windows, and how much space is on it? 900 and something gigabytes. And you're like, damn it, I just got ripped off. Well, what happened? Well, it's partly the OS, but the hard drive manufacturers use Gigabyte to mean the power of 10 system. And the operating systems, well, they've changed this to match, would use the power of 2 system, okay? And so what you thought was a gigabyte was in fact really only 930 whatever megabytes or whatever. And this caused like class action lawsuits and stuff like that. Anyway, huh? Even though, like, if you look on the box of a hard drive, it's got a little asterisk, and down in tiny print it says, you know, a gigabyte is defined as 1 billion bytes. No, which is why this isn't a big issue, but yeah, okay. All right, so sorry for my digression there. Pointers, what else do we need to talk about here? Well, if I can do, what really is, a string? A string is an array of characters, okay? Could I have an array of other types of objects? Like what? I could have an array of integers. Okay, now this is one place where we have to be a little bit careful, okay? Because if I wanted to have an array of integers, okay, how wide is each integer going to be on this thing? How big is an int? How many bits? An int? Like either 32 or 64 bits, right? Okay, how wide is a character in bits? In bits, not bytes, sorry. Nope. Yeah, you just keep spitting out numbers and eventually you guys will hit it. It's 8 bits, 1 byte. Okay? Okay, because how are characters encoded? Which is an 8-bit scheme. Okay? So ASCII can only encode 8 bits worth of stuff, which is 256 different characters. Okay, do you want more than that? Then what do you have to do? Use Unicode, and that's a nightmare. Okay, well, from a programming standpoint. Okay, so when I'm counting through, so like let's define here an array of numbers. Okay, so let me come down here, and let's make an array. Let's say int my array, and let's just put 4 things in it, okay? And well, here, and let's define it to be, how about, the what now? Yes, the curly braces. Okay, so what's the definition here? Well, first off, what's the name of the array? Well, I called it my array, whatever. How many things does it have in it? 4 is how I'm defining it. And what type of object are each of the things? They're ints, okay? All right, and so I've got here 1832, just whatever, right? And so what can we do with this thing? Well, okay, so here's one major difference between these and strings. How do we know if we've hit the end of a string? Yeah, is there such a thing for an array? Not really. I mean, it'd be nice if there were something that told you you were at the end of the array. Okay, and maybe we could sort of recycle the idea of a null terminator. Okay, but this is going to be sort of an issue in terms of keeping up with the length of these things, because of therefore how much space they're going to take up into memory. Okay, good? We? All right, so let me just define that array, and let's not actually do anything with it yet. We'll just store it in memory. All right, so let's compile this, and then I'm going to GDB, and I'm going to break right here at line 27. Okay, just before the program terminates. Okay, and let's look in memory, and what do we see? And sorry, it's down there at the bottom. Huh? Yeah. Do we see them down there in memory? Yeah. Right? 1832. Okay, great. All right, so here's where we have to be a little careful though, because if I'm going to, so what is the location of the first value of this thing? The 1. 050. Okay, what's the location of the 8? Okay, good question, right? What do you think? Okay, too big. Okay, what is 051? 051 contains these 2 zeros. Okay, so 050 contains 01, 51 would contain the next 2 zeros, 52 would contain the next 2 zeros after that, 53 would contain the next 2 zeros out of that. So how much stuff is here? How many bits are there? Huh? There's, how many bits or bytes? Just, it's 4 bytes. Okay, because each hexadecimal symbol is a nibble or 4 bytes. Okay, so 4 bytes for the 1, and therefore what's the memory address where the 8 is? 054. Okay, what's the memory address where the 3 is? 058. Okay, and the memory address where the 2 is? Ah, gonna nail you guys. Come on. What's after 8? I'll take 05C, thank you. Because, why? Why is it 05C? Hex. We're counting in hex, damn it. Right? What? Yeah, because 8, 9, A, B, C, right? Have you guys done hex before? No? You'll catch on. It's really not rocket science. Okay, so how wide are these things? Yeah, how big the numbers? How many bits were stored there? Uh, it was 4 bytes, 32 bits. Okay, why was it 32 bits? What kind of integer did I declared it as an int? What about if I wanted these things to be 64 bits? Yeah. So let me just make that change here. Yeah. No, not by default. Okay, now look at it. Huh? Well, except where's the 8 now? Yeah. So right, difference in terms of its memory storage. Okay. All right. So I'll come up with some other diabolical assignment for you guys, and I will see you next week when I get back. See ya. Oh, yeah, sorry. Hold on. This is important.